Us about the Coulomb gas of random supergravities.
Thank you, and let me start by thanking the organizers. It's been a great conference. I learned a lot from several of the talks here. This work is based on a paper that came out in December, together with Liam McAllister, who talked about the paper 2 days ago, and also Tim Brase, who's also at Cornell. And it's also based, most of it actually comes from a paper that's coming out soon, probably next week, maybe the week after, about supersymmetric critical points in supergravity. Right, so the outline of my talk is this. I'll talk about what we call random supergravity, what assumptions we're making in order to make a statistical treatment of the landscape. I'll then talk about Coulomb gases and random matrix theory, and since this is a 10-minute talk, I'll talk both very quickly and very briefly about it. Then I'll talk about supersymmetric vacua and their statistics, and then I'll finally mention some stuff about de Sitter vacua. So the statistical study of the landscape that we're basing our work on was pioneered by Denef and Douglas, and some other work by Douglas several years ago. What they imagined was that if you have a potential landscape, say you get some supergravity in 4 dimensions, which is a very complicated supergravity, you can have many different vacua, and in particular you can have many different critical points. So if you want to study critical points and vacua statistically, well, what you first do is that you mark all the critical points out, and at all these critical points you compute the value of the superpotential, the value of the F term, and the value of the supersymmetric mass matrix, which is 2 derivatives on the superpotential, and similarly for the Keller potential. Now, once this is done, well, you have to fix the Keller gauge and you have to fix the diffeomorphism invariance, but you can construct a distribution of the collection of the superpotential, the values of the superpotential at all these different critical points, and similarly for the F terms and 2 derivatives on the superpotential, which is the fermionic mass matrix. So if you want to do a statistical study of this, you can then start to think about the continuous distribution of these different quantities. So here I've marked the distribution of the superpotential omega mu theta. So mu here is the mean and sigma is the standard deviation. This is some complex distribution. And similarly, there could be other distributions for the F terms and for the supersymmetric mass matrices, but I didn't want to put out too many indices. But this way you'll get some distribution. Now the key point to the study that we've done and why it's even interesting is that for many interesting questions, the details of the distribution omega actually doesn't matter. So for instance, if I computed an element of the fermionic mass matrix and found that it had a flat distribution from, say, well, I think it's square root of 3 to minus square root of 3, and then I did some study with that, well, a lot of questions are actually unchanged if the distribution would change completely. These questions are those that are protected by the universality of random matrix theory, namely questions that are concerned with eigenvalues and eigenvectors of large matrices. So let me talk a bit about random matrix theory. What we imagine is that we have some matrix model. So we have, say, a Hermitian matrix M, and the entries of this matrix M are independent and identically distributed with some prior distribution function M, F naught. Here F naught would be, say, the uniform distribution or the Gaussian distribution, for instance. The key assumption, though, is that they're independent and identically distributed. Now, you can diagonalize this matrix, and you get some eigenvectors, you get an integration of the eigenvectors, and you get an integration of the eigenvalues. You can integrate out the integration of the eigenvectors, because it only gives some volume. The key thing is the eigenvalues, and instead of having an independent measure for the different entries of the matrix, you now have a joint probability density denoted f of lambda 1 to lambda n for an n by n matrix, which is the joint probability distribution, and it has an interaction between different eigenvalues. So for instance, for the Wigner ensemble, for just an Hermitian matrix, it looks like this. So it has it's e to the something, and this prefactor to this something is beta, and it is an inverse temperature. It's called the Dyson index. It has temperatures 1, 2, and 4, or inverse temperatures 1, 2, and 4, if the numbers are real, complex, or quaternionic. There's a potential for the different individual eigenvalues, and there's also an interaction between the different eigenvalues. Similarly, if I would take a matrix and square it, this matrix that I square doesn't have to be n by n, say it's n by l, then the probability distribution has a linear potential, it still has an eigenvalue interaction, and it can also have a different term. I'll mention a distribution called C1, which is a 2n by 2n matrix, which is off-block diagonal. So you have some symmetric tensor, two tensor up here, and a complex conjugate. In this case, you get a partition function where the weight is given by this expression. So it's a quadratic potential, just as the Wigner case. It has some eigenvalue interaction and another force term, which actually pushes you away from the origin. Now, once you have this, you can start to ask questions like, what's the typical bulk distribution? What's the empirical distribution of eigenvalues? For the Wigner case, you've seen this plot at least twice during this conference, in Gary's and in Liam's talk. It's the Wigner semicircle of eigenvalues of a Hermitian matrix. This is the real Wishart ensemble. It's the eigenvalue distribution of one of these square matrices. And the C1 ensemble looks almost like a Wigner matrix. The only particular feature it has is that it has a cleft here, so it drops to 0, very close to 0. Now, these joint PDFs, as you might have noticed, look very much like an actual partition function of a statistical system. And one can get a lot of mileage out of actually using statistical techniques on these ensembles. So the logarithmic potential that all these different joint probability densities had can be interpreted as an electrostatic interaction in 2 dimensions. The eigenvalues are real because these matrices are Hermitian. So the eigenvalues are confined to 1 dimension, but they're interacting with some 2-dimensional Coulomb static force. And then they're pulled to the origin by some quadratic or linear potential. And for the model, the Wigner plus Wishart model that Liam mentioned in his talk for n equals 1 supergravity, we've actually obtained this function, this joint probability distribution function. So we have the techniques of statistical physics, and we can employ them on questions about on the mass spectrum. But I want to talk primarily about supersymmetric vacua. The supersymmetric mass matrix in n equals 1 supergravity, F-term supergravity, is given by this expression. Here, C is the fermionic mass matrix. It's symmetric. It's given by 2 derivatives on the superpotential. So the mass matrix is C bar, C bar C, and then there's some off-diagonal part. And there's also a shift to negative values. So we've obtained a mapping that we'll present in this paper soon, where we take this Hessian, we solve it exactly, and we map it to a different ensemble, to an ensemble of real Wishart matrices that aren't really associated with the Hessian in an obvious way, but the joint probability distribution functions match. And then we can phrase any question we have about the Hessian to a question about this other ensemble. Here, I will CAB, the fermionic mass matrix, obviously has a scale, the supersymmetric mass scale, so I'll factor this one out. And the result will depend on the relative ratio of this scale to the gravitational mass. So this is what the spectrum looks like. Suppose that we have large supersymmetric masses, so that the gravitational mass is small and the supersymmetric masses are large, then we're almost in Minkowski space. So we have 2 branches in the spectrum, one colored red, one colored blue. And for each eigenvalue in the blue branch, there's an eigenvalue almost at the exactly same spot in the red branch. So they're compared. This is, of course, what you would expect from global supersymmetry. If you give a scalar or a chiral superfield a supersymmetric mass, both the real part and the imaginary part get the same mass. That's what's obvious in this picture, or that's what you get from it. If you start to increase the gravitational mass, well, the first thing you see is that you get some little support on negative values, and there's some kinks showing up in the spectrum. This gets more pronounced as you increase the value of the gravitational mass. I should say that the black line here is nothing we put in, but it is the Brighton-Lone-Friedman bound. So as you know that in ADS, fields with tachyonic masses are stable as long as they have masses above the Brighton line of freedom bound. This comes naturally out of the theory. So in this case, where m SUSY equals to w, the spectrum has a square root, 1/square root divergence close to the Brighton line of freedom bound, but there's nothing to the left of it by consistency. You see also here there's something funny going on. It's a very strange spectrum. It doesn't look like a semicircle or anything simple. If we continue to this process of increasing the gravitino mass, or the ratio of the gravitino mass to the supersymmetric mass scale, we see that the entire spectrum shifts to the left. So here, all the eigenvalues are tachyonic. There's also this cleft that appears, and it just continues. And here you see that what actually occurs at large values of the gravitino mass with respect to the supersymmetric mass scale is something that almost looks like the C1 ensemble, which can be understood from just looking at the mass matrix. All right, so I wanna spend 2 minutes talking about uplifting to the Sitter vacuum. So Liam, let me just summarize our results actually. So the spectrum, if you would ask one of these ADS vacua that's typically unstable to not have any tachyons, but still ask this question in ADS, this is the spectrum that you would see. So this is the spectrum in ADS, but conditioned that no eigenvalues are negative. So it's peculiar. The probability of obtaining this is suppressed by e to the minus n squared, and then the w squared over m SUSY squared. This is an exact result, by the way. So let me go through the summary, both of Liam's talk and of my talk, because we've talked about essentially 4 different cases. The cases I've talked about was more brief, of course. So for generic critical points with spontaneous supersymmetry breaking, we've obtained that the probability that the smallest mass is greater than 0 goes like e to the minus c n squared. The spectrum has a sharp peak for the fluctuated, the positive definite solutions, the vacua. If you go to an approximately supersymmetric critical point, the number of vacua are instead given by the area under the curve of the light blue histogram here to the right of 0 over the area to the left. It's a small number, but it scales like e to the minus n log n. So it's much more probable to have a vacua in this region, even though it's not really likely or generic. So in this supersymmetric breaking by uplift, the scaling that I talked about for tachyon-free supersymmetric vacua, in case m SUSY is smaller than nw, looks like this, as I said. But there's a different region, and that's when you increase the supersymmetric masses in ADS. And in this case, if you increase it enough, namely greater than nw, all the masses here in the ADS vacuum are to the right of 0. And furthermore, since there's a hierarchy between the gravitino mass, which is kind of the amount you have to uplift when you go to Minkowski space or a small de Sitter vacuum, small cosmological constant, one can estimate that these will be rather robust under uplift. But that last statement is more vague, since it contains some assumption about the uplift. But this statement is definitely true. So I'm out of time. So I'll just say that random matrix theory offers some really powerful and actually very enjoyable techniques for addressing a wide range of questions. Thanks.
Questions?
Can you remind us what n was?
Oh, yes, sorry. N is the number of chiral superfields. So number of light moduli.
So which scenario is number 3, case 3?
Case 3.
The one
You mean
minus n squared.
This one?
Yeah.
Yeah. This one is, for instance, suppose that the supersymmetric masses are stabilized at the order of the gravitino mass in ADS. This is what you would do maybe in KKLT or something like that. Then, yeah, this is the ADS minimum. Yeah, this is not the typical spectrum at the ADS minimum, but this is us going to the ensemble, the full PDF, the full Young probability distribution at the ADS minimum, and requiring that the smallest eigenvalue is 0 or greater.
If you want to explore the landscape of theories with higher supersymmetry, like maximal supersymmetry, can you also do random matrix theory, or theories with a lot of symmetry are not random, or what?
No. I mean, I think it would be possible. Absolutely. It would probably look very different. We've looked at some simple tweakings of the n=1 thing, like we're taking special Keller geometry for the field space. That didn't help, but it's an interesting question, and one can definitely do it.
Yes, thank you, David.